Imagine a man living back 400 years ago. He comes in from a hard day's work and decides he needs to get a drink. However, instead of walking to his kitchen and turning on the faucet like you and I would do today, he is forced to go to the city well, throw in a bucket, and then heave up the water using his own strength. However, at that time, that was the only method they had in order to gain a fresh water supply without having a river directly next to their city. This would all change with the development of the suction hand pump. The suction hand pump's purpose is to use the forces of nature and the forces of physics in order to reduce the amount of manpower needed to pull up water. Now, I know the laws that govern the suction hand pump are rather complicated. Its actual mechanism and how it works is rather simple. As you can see here on the very top is the force bar. This is where you put the energy in and start to pump. Connected to that force bar is a piston rod. This piston rod goes up and down as you push the force bar up and down. At the very bottom of the piston rod is a piston. This piston is circular and has a sealed O-ring. This allows for your suction force to happen. On the top of the piston, right there is a check valve. This is your first check valve, which opens and shuts as the force bar goes up and down. And on the very bottom is your secondary check valve, which opens and shuts due to suction force. Now, before I can explain to you how this all works, I kind of have to explain how the laws work. So first off, you have the first check valve. Now, there's nothing opening and shutting it. No electricity goes through the pump. The only thing that guides this check valve is the laws of physics. So you can imagine that this check valve is down here. And due to Newton's third law, which states that an object at rest would like to stay at rest, and an object in motion would like to stay at motion, this check valve wants to stay down here if it possibly can. However, as you force it up, as you pump up and down the force bar, it starts to rise. However, it doesn't want to rise. It wants to stay down here. So it's going to stay closed to stay as close to this point as possible. And eventually, it gets all the way to the top, and you start to force the force bar back down. Now, this check valve is up here, and it wants to stay up here now. He likes it up here. But as you force it back down, it's going to try to stay as close to that point as possible, and it'll open up. And that's how it opens and shuts. The secondary check valve down at the bottom opens and shuts due to a suction force. This suction force is guided by the ideal gas law theorem, and this theorem states that pressure times volume equals the amount of moles times a constant times temperature. Now, I know that seems really complicated, but all you need to get from this is the moles in a closed system will stay the same because you're not adding particles. The R is going to stay the same, and the temperature is going to stay the same. So all three of those are going to cancel, making pressure equal to 1 over volume. Now this states that as your volume in the closed system increases and your piston rod goes up, the pressure in this system is going to go down and decrease. Now as that pressure gets lower and lower and lower, as the system gets bigger and bigger and bigger, the outside forces that have a higher pressure are going to try to get in there. This makes the bottom check valve open to try to get to that lower pressure system, and the water starts to rise as the suction continues. By the time your piston reaches the top, that suction force closes, the valve shuts, and now that water is trapped in this bottom valve. Now as you push back down, the piston starts to close, that top valve opens due to Newton's third law as I explained before. The water goes to the top into this top container and then is trapped once again. So you have your piston down here now, and as that piston rises, top valve shuts, the bottom one opens, allowing in, and the top water that's up here goes out the spout. Now I know that's really complicated and can seem rather confusing, and that is why I brought in this air pump to kind of explain it. This air pump operates much the same way as a suction hand pump does. As you can see here, this would be your force bar, this would be your piston rod, inside this container would be your piston with a check valve on it, and down here would be your secondary check valve. Now the only difference between this and your suction hand pump is that the check valves are underneath instead of on top. So as you draw up the air into the system, this check valve is going to stay as low as it possibly can, so it's going to open, allowing air from the outside into the system. And once it gets to the top, now you have a closed system from here to here. As you push down, the pressure in this system is getting increased because the volume is decreasing. This pressure causes this bottom check valve to open, pushing the air out into your basketball. As you pull back up, the pressure stops, so this bottom check valve closes, and the top close and the bottom or the top check valve will open, allowing more air into the system, and so forth. So much the same way, you have your suction hand pump. You start to pump it, check valve will open, allowing air in, gets to the bottom, suction force happens, water comes into the system, goes into your top chamber as you come back down and out the spout. Now this very simple mechanism has been used throughout the United States in many different ways and throughout time. However, with modern technology, it's becoming less and less prevalent and is still widely used in very remote areas or in countries that aren't quite as developed as we are. The most important thing about the suction hand pump, it was the first of many inventions that have allowed us the luxury of being able to walk into our kitchen, turn on the faucet, and have a cold drink of water.